be at physiological pH because there's an unshared pair of electrons there.
Okay.
Right? The reason I didn't draw it, now we have to talk about why creatine, why is this bond higher energy? What is it about this phosphoamide bond in creatine? Because creatine has, do you recognize this group? You might want to spin that thing a little bit.
Sorry.
Yeah, there we go. There we go. Right? What does this group look like? Where have we seen that group before? And I will tell you, it's a guanido group. Again, I'm supposed to be way past this. I've gotten caught in details I think are cool. We're supposed to be done with this whole thing. I was not supposed to talk about that. I'm not supposed to talk about what I'm ready to talk about now. This is why we're always behind in this class. I think this stuff is cool. I'm just telling you. Okay. So, where have we seen this 3 nitrogens and a carbon before? What? In arginine, yeah, right? That's the guanido group that we've seen in arginine. And what do we know about that group? You got a C, N, N, N. Right? If we put say we go ahead and protonate that one. If we just look at the guanido group itself, we can get something like that. Why did I do my unshared pairs of electrons that way? There, that one looks better. Right? What do you notice about all 3 nitrogens?
Resonance.
Each one has 2 hydrogens on it. And remember, let's see, what's the hybridization of this carbon?
sp3.
sp2.
The
Yeah,
planar
3
one.
groups, sp2. sp2. But remember, even though this looks like it has 4 areas of electron density, because it's next to an sp2 hybridized carbon, these 2 nitrogens also get pulled sp2. So the unshared pair of electrons can participate. And so we have, right, if we drop this down and this down, we get the double bond there. If we drop this down and this down, we get the double bond there and the positive charge there. So there's resonance, even resonance, all the way through that guanido group. So, back to our things of what stabilizes the products that makes these things high energy. If nucleophilic attack by the ADP is here, to transfer the phosphate to the ADP, why is that favorable? Why then does this become a good leaving group, the creatine molecule?
More resonance.
Right? It is a
Energetically.
Yeah, we get an energetically favorable nucleophilic acyl substitution. Our leaving group is stable because it is a stable, weakly basic molecule or ion. In this case, resonance stabilized ion. Right? So when this acts as a leaving group, we get the potential for this resonance stabilization of this guanido group, and so that's what makes it high energy.
Could you also say that there's less charge separation? If that part's if that nitrogen's positive? That's mostly why I asked.
Well, if this is positive, then we've actually got an attraction there.
Okay.
Right? Not a repulsion like we normally see.
Okay.
So it's the resonance stabilization through the guanido group, which ultimately leads to that. stabilization of the products, which makes the reaction energetically favorable. Right? Why did I work so hard to draw glucose 1-phosphate? I had glucose 1-phosphate. With the phosphate in its, right, stuck in that axial position. Okay? So, this is a phosphate, even though it looks like an, it is an ester, it is the structural steric strain caused by the different conformations of the potential chair structure of the six-membered ring that makes this unusually high energy for an ester linkage. Okay? Then we said ATP going to the pyrophosphate. No, the pyrophosphate fit in there because the pyrophosphate is somewhat resonance stabilized, but you still have a lot of charge density. Then we have the relatively equal in energy phosphoesters of fructose 6-phosphate and glucose 6-phosphate, where this is equatorial, held away from the ring, so there's not as much strain. And then the glycerol 3-phosphate, which is lower energy because it doesn't have the same kind of strain that the ring systems have. Seems like a lot of work. But do you see the way we can take these things, these arguments, and these structural things we talked about in organic chemistry, and apply them in ways that make the things that we may have talked about in physiology and accept it on face value? We can make chemical arguments for why that makes sense. Right? Why, yeah, okay, that's good. I agree with that from a chemical perspective. Okay? I don't have to just believe it when Dr. Zimmerman told me something. Right? Any questions about that? I think the book has some structures. We can talk about them. Oh yeah, the other group of things that are high energy. Okay, so we've done phosphates. So let me jump down to the other things that we classify as high energy molecules. Which is these? This is acetyl-CoA. Right? So, acetyl-CoA, right? Here's our acetyl group. This could be a hydrogen, so this is an acetyl group. This sulfur, this beta-mercaptoethylamine group, is actually just decarboxylated cysteine, right? The amino acid cysteine. So you just take the carboxyl group off of here and you get that group. So that group's made from cysteine, the amino acid. Then we get a pantothenic acid group. Right? Those of you that read the side of your Pop-Tarts box in the morning, right? Pantothenic acid is always in there. It's one of the B vitamins, B6, B4, one of the B vitamins. Do you sit around and read your cereal box in the morning?
I used to.
And the shampoo bottles? Okay.
Shampoo bottle.
I'm not awake enough to read my shampoo bottle. But when I used to eat cereal, I read my cereal box every morning. I don't eat cereal anymore. Not very often. So anyway, pantothenic acid is one of those vitamins that you take. And remember, a lot of the things that we take as vitamins are The ones that are organic compounds are often things that we need in this kind of role, to play some structural role in some kind of coenzyme or a molecule like that. So that's there. Then we get an ADP, right? So we have ADP, right? Ester, anhydride, ester. So there's an alcohol end on the pantothenic acid. The acid end of the pantothenic acid is linked to the nitrogen of the mercaptoethylamine. So what kind of bond does that become? Carbonyl to a nitrogen?
Amide? No.
What is it?
Is it an amide?
It's an amide. What do biologists call that kind of bond?
Peptide.
It's a peptide bond, right? So biologists talk about the peptide bond in this, right? So it is a typical amide type linkage. What kind of bond is this? This linkage?
Phosphoanhydride.
Phosphoanhydride. So there are actually a few bacterial species that use the hydrolysis of that bond as an energy source in some membrane transport processes. Right? So it is a high energy bond. Mammals don't use it as a high energy bond, but some bacterial species do. So this is acetyl-CoA. All of this, right? All of this is just used for enzyme recognition. The real meat of the chemistry is right here for coenzyme A. Right? This sulfur group. Okay. Sulfur versus oxygen, right? This is like Mad Magazine, Spy versus Spy. Right? Sulfur versus oxygen. Which is the stronger acid? H2O is, you're going with water as the stronger acid. We're sure about that. Or we just believe in Jordan.
No, I don't know. Like it's about.
Right. It's higher on the periodic chart. Right. But remember, electronegativity works going left to right on the periodic chart. Right. The more electronegative atom creates a stronger acid than the less electronegative atom. But as we go down, bigger atoms can accept the negative charge better than smaller atoms can. So hydrogen sulfide is actually the stronger acid because the sulfur being bigger can accept the negative charge left behind better than the oxygen can. Which is the stronger base? Are you sure? You guys were pretty sure last time. Why do you say the hydroxide ion is a stronger base than the hydrogen sulfide ion? What? It's more electronegative.
It's smaller, so it doesn't deal as well with the charges as sulfur does.
Right? If oxygen doesn't deal with the charge as well as the sulfur does, then that means it's going to go out more actively looking for something to balance that charge. Right? And oh, by the way, if this is the weaker acid, then that has to be the stronger base. Yeah, right? We got that whole reciprocal thing. So the hydroxide ion is the stronger base. So, right? What do we know about negative oxygens as leaving groups? They're bad leaving groups. But if negative sulfurs are weaker bases, then what do we suspect